So we want to know, we have studied, having studied the continuous time signals, its Fourier series and so and so, and then afterwards, the discrete time Fourier series, right? So all the while we have been teaching from first module on that there are continuous time signals and then there are discrete time signals, right? But then real world signals which are we have seen are always continuous time in nature, right? Real world problems are all continuous time in nature. Okay, then where do we get this discrete time signals? Where do we get this discrete time signals? Right, because somebody has to convert. So the entire discrete time signals are never real world in nature. All the real world signals that occur in nature are continuous time signals, signals which vary continuously with respect to time. But then the digital technology, right? The digital technology, the availability of digital memory, very cheap digital memory, and the digital signal processing, the digital communication, right? So all the advantages of digital communication along with digital signal processing provoked the engineers, the scientists, to convert the data which is continuous in nature into something which is digital, okay, into something which is digital, okay. So that is why we are using the digital signals, okay, the discrete signals, sorry, okay. So are you getting my point here? The real world signals are always continuous in nature, okay, the real world signals are always continuous in nature. But there is a problem that the systems which are processing the continuous time signals, like your amplifier, your analog radio, the whole analog communication or analog storage, right, is not at all cost effective, as it uses a lot of copper and so many bulky equipment. So some 20-30 years back, with the advent of the digital communication and digital signal processing, thanks to the VLSI technology, right? So the processing in digital domain became much more convenient, providing us so much facilities. So people were forced to convert data from analog to digital, right? So scientists, the people were forced to convert the data from analog to digital, so that they can use the digital signal processing, so that they can use the advantages of digital signal processing, right? So you might remember in old TV of yours was so big, the old radio which your grandpa used, which was so big, right? Even the tape recorder, whatever we used, they were so bulky in nature. And nowadays you can see the tape recorder has been replaced a very small iPod, right? A very small tiny device. The entire TV has become flat, right? So all these things happen, and our dish antenna, right? The entire TV receiver has become so small because thanks to the digital technology, right? So what we actually produce, the real world signals are analog in nature. What we understand is also analog in nature. So, but the thing is, the digital signal processing is much more cost effective. So what we have to do is, so there is always a situation where we have to convert the data from continuous time to discrete time. So why do we convert the data from continuous time to discrete time? Not because it's a tough task, okay. So the converting data from continuous time to discrete time is called as analog to digital conversion. The process is called as analog to digital conversion, okay. So once the data is digital, we can always use the digital signal processing, we can always use the DSP concepts to process the data. And once my data is processed by this black box, then afterwards what we can do, yes, now the data is digital. Now this data will be converted back to once again analog by using the DAC, the digital to analog converter, by using DAC, the digital to analog converter, to get my analog signal y of t, right? So this is the usual thing that has been happening, okay. But we have studied the analog, we have studied digital, we have studied continuous, we have studied discrete. But how does it work, by the way? How does it work? How signals are converted from continuous to discrete? That we did not study. So sampling theorem sets the rules. How do we convert the signals from continuous to discrete? Okay, say there is a signal here. See, this is a particular signal. Now I want to convert this particular signal to discrete. Why do I do it, by the way? What is the problem with the continuous signal? First thing is, if at all take a very small unit here from time instant t1 to t2, you can see it contains infinite amount of signals that exist at each and every instant of time, right? Infinite amount of signals. So if at all I want to store them in a memory, right? So as I told you, the analog memory, the magnetic disk is like very bulky. If at all I want to go for a digital storage like your SD card or your memory card, whatever it is, you can see, since there are infinite values, okay, you can see at each and every time instant there are values existing, and there are infinite amplitudes. You can see there are infinite amplitudes here also. Okay, so first thing is you need, so are you getting my point? If at all there are four amplitude levels, 1 volt, 2 volt, 3 volt, 1, 2 volt, 3 volt and 4 volt, or say there is 0, there is 1, there is 2 and there is 3. Okay, say there are four amplitude levels, then I can manage with 2 bits, right? 0 0 for 0, 0 1 for 1, 1 0 for 2, 1 1 for 3, right? If at all there are 1 to 4 amplitude levels, I can manage with 2 bits. If there are 8 amplitude levels, say from 0 all the way to 7, from 0 to 7, then I can go for 3 bits: 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 0 0, 1 0 1, 1 1 0 and 1 1 0 and 1 1 0 and 1 1 1, right? So I can use 3 bits. If there are 4 levels, I need 2 bits. If there are 8 levels, I need 3 bits. If there are 256 levels, I need 8 bits. Getting this? If at all I want to represent some amplitudes digitally, I need, depending on how many voltage levels you want, the more the number of voltage levels you want, more the number of bits you need. The problem with analog notation is two. There are two problems. First thing, amplitude analog notation has lots and infinite number of amplitude levels. Infinite number of amplitude levels which need infinite number of bits for the representation. That is first problem. Second problem is they exist in each and every value. They exist at each and every value, which also needs infinite memory. Okay, these two problems provoke us to go for digital representation. When you go for a digital representation, what does a digital representation means? Digital representation means something that it contains only finite number of amplitude levels. Okay, it contains only finite number of amplitude levels. Okay, something like 1 volt, 2 volt, 3 volt, 4 volt, okay, and so on. So amplitude levels are finite, and the samples occur only at finite intervals of time. Okay, the samples occur at finite intervals of time. In between these two amplitude levels there is nothing. Okay, in between the amplitude levels there is nothing. Okay, and you can see the amplitude also, the amplitudes also, they are finite in nature. The amplitudes are also finite in nature. For the time being, in this semester we are bothered only about how to select the amplitude. At what rate shall we select the amplitude? What is meant by rate, by the way? Now suppose there is this particular entire duration. Okay, there is this particular entire duration from say 12 o'clock, okay, 1 o'clock to 2 o'clock. Okay, there's this duration from 1 o'clock to 2 o'clock. Okay, and I want to now take the signals. Okay, say there is this temperature variation in a furnace, and I want to take the samples. Now, how frequently shall I take it? Okay, from 1 o'clock to 2 o'clock, there are several options. I can take one sample every 1 minute. Okay, if at all in 1 hour, if at all I take one sample in every minute, then totally how many samples do I need? I need 60 samples. Okay, if at all, otherwise what I can do, otherwise what I can, so 60 samples means it needs 60 memory locations. Okay, 60 memory locations. Okay, otherwise if at all I decide to take one sample every second, then how many samples do I need? I need 60 minutes totally, and each minute contains how many seconds? By the way, each minute contains 60 seconds, right? So these many number of samples, that means I need that many number of memory locations also. So if at all I decide otherwise, I need to take a sample every 1 millisecond. Okay, then I need how many? Each second into millisecond, then I need much more, right? So it doesn't, it sounds foolish, right? On one side we wanted to limit number of memory, but then here see less amount of memory. What is the problem, by the way? What is the problem with taking too less number of samples? See, whenever we take samples, it means we do not know the value in between. We don't know the value in between, right? So when you convert the data from continuous to discrete, when we convert the data from continuous to discrete, the value in between we don't know, right? The value in between we don't know. That is why there has to be some guideline. What is the minimum samples that we need to choose between two, what, how much gap shall we given between two alternate samples? Okay, so that at least the frequency components are retained. Okay, so that at least the frequency components of the signals are retained. Okay, so is the class getting much slower and boring here, by the way? I started feeling so. Okay, let me continue in a little faster pace. Okay, so what we are trying to do here is we are trying to relate the continuous time x of n with discrete time x of t. Okay, okay. Sorry for that. Okay, yes. So how do we convert the data from continuous to discrete? See here, you have a signal x of t. So what I will do is, say there is this patient, okay, who has been admitted to an hospital. Okay, so he is suffering from fever. Okay, now that this is COVID time, I think it makes sense. Okay. He is suffering from fever. Okay, then the question is, if at all he is suffering from fever, he is there for an entire day. The question is, how frequently would you like to take his temperature? How frequently would you like to take his temperature? So the frequency with which the samples are taken is called as the sampling frequency. And the gap between which, right, so you can, the nurse will come and she will take samples at 1 o'clock, then at 2 o'clock, then at 3 o'clock, then at 4 o'clock, then at 5 o'clock, right? The sampling interval, I would say, is 1 hour. The sampling interval is, say, 1 hour. And sampling frequency once in an hour, 24 times in a day. Okay, that's how what we'll say. Now, how do we represent these things, by the way? Yeah, real world signals are fine, but how do we represent it in actual thing? So the actual representation is something like this. So if at all I multiply my signal x of t with a pulse train, do you know what this thing is? This is nothing but, you can see these are so many impulses, right? You can see these are so many impulses spaced at a interval tau, 2 tau, 3 tau, 4 tau, and so on, with a spacing of tau, and existing from minus infinity to plus infinity. If at all I multiply this by this, I will end up getting the discrete time signal. Okay, I will end up getting the discrete time signal. So this is called as impulse sampling. Okay, so how do the expressions look like? Let us see how the expressions actually look like. So here what has happened, my signal x of t has been converted to a so-called discrete time signal here. So what did I multiply this with? I multiplied this x of t with a pulse train. You can see this is an impulse delta t occurring at time instant tau, right? This is C, this is my N. So this occurs at instant 0, tau, 2 tau, 3 tau, 4 tau, minus 2 tau, minus 3 tau, minus 4 tau, and so, right? Right, so and so. Okay, so what has happened by multiplying my signal x of t with this impulse train p of t, I have got this particular thing x delta of t, which looks discrete in nature, now we are interested in the frequency of all the things. Now we are interested in the frequency. What happened here? The multiplication. Now I multiplied my continuous time in x of t with p of t, the pulse train or the impulse train. Okay. So what happened in the frequency domain? So the multiplication in the time domain resulted in the convolution in the frequency domain. Multiplication in the time domain resulted in the convolution in the frequency domain. X of omega is the Fourier transform, the frequency component of x of t. P of omega is the frequency component of my impulses, okay, which also happen to be the Fourier transform. See, I have not covered this particular topic, sorry, okay. The DTFT of the pulse train is a pulse train in the frequency domain also, okay. So we will not get much into this. We'll just see the frequency spectrum of the sample signal. How does it look like? See, it is represented by this particular wave here. Let us see what does this representation actually mean. What does this representation actually mean? Okay, so here it is. So I started with a continuous time signal, right? So this was my continuous time signal. Okay, this was my continuous time signal x of t. Okay, my continuous time signal x of t, whose Fourier transform is this. Okay, whose Fourier transform is this. Now what all things does it have, by the way? So this Fourier transform normalized, this some random shape has been assumed here. Okay, so what this representation means is, now this particular signal here is having maximum signal frequency of omega, not omega, some w. Okay, omega is the frequency. So it does not say something like 100 hertz or 200 hertz. There are so many frequency components in this particular signal. Okay, but the maximum signal frequency does not exist omega. Okay, okay. Now what does this indicate? What does this indicate? Now see, this was my original signal. Okay, this here was my original signal x of omega, x of t. Okay, and that's Fourier transform. Now this here represents the Fourier transform of the sampled signal. This here represents Fourier transform of the sampled signal. Okay, so what just happened here? This is the Fourier transform of the sampled signal. Now see what has happened is, after sampling, what has happened is, this particular signal here is being replicated. This particular signal is being replicated. You see, this is the original signal, right? This is the original signal, which is here also. This signal is here also. The same thing is replicated at WS. You can see this signal only is replicated at WS, replicated at 2WS, replicated at minus WS, minus 2WS, and so on. Okay. Now what is this WS? WS here is the sampling frequency, right? In the previous diagram, do you remember, in the previous diagram, whatever we saw, we had our signal existing at interval, right? See, we have taken samples at an interval. The spacing between them is what? The spacing between them is tau. Okay, the spacing between them is tau. Then how frequently do we take the samples? So the sampling frequency is given by frequency is equal to 1 divided by time interval, right? If at all I represent this frequency in terms of radians, then I multiply by 2 pi also. So omega s indicates 2 pi by tau. Omega indicates 2 pi by tau, which is the sampling frequency. So what has happened here? Once you convert the signal from continuous time to discrete time, The signal not only contains its original frequency components, but also its replica will be repeated at WS, 2WS, 3WS, 4WS, minus WS, minus 2WS, and so on. Got the thing? So this is the reason why your continuous time x of t has a continuous time Fourier transform which is aperiodic in nature, whereas the discrete time x of n, the discrete time signal x of n is having the Fourier transform which is periodic in nature, which repeats, right? Have you seen the discrete time Fourier transform repeats? Okay, because whenever you convert a signal from continuous time to discrete time, you get the replica of the original signal. Now the question is, what should be my sampling frequency? Now the question is, what should be my sampling frequency? Less number of samples means less number of memory, less number of power consumption, right? But less amount of clarity. More number of samples means more amount of memory, but more amount of clarity, because we will get all the data, right? We'll get most of the data. Now the catch is in the frequency domain. So the thing is, we should select a frequency. Now see here, if at all this I chose a sampling frequency WS, you can see here in this particular case I have taken WS equal to 2 into W, right? See, this was W, right? You can see here this WS is exactly equal to 2 into W. Then my sampling frequency is twice the maximum signal frequency. By that, what happens? The spectrums are just touching each other. See here, spectrums are just touching each other. Okay. If at all I might take my sampling frequency less than, if at all I might take sampling frequency here less than 2W, less than 2W, then what's going to happen? The triangles are going to overlap. The triangles are going to overlap. You can see here, the triangles have overlap. So what happens with that, by the way? What is the actual idea? You take the signal, convert it, right? Take the continuous time signal, convert it to discrete, right? You take the continuous time signal, take the continuous time signal, and you convert them to discrete. Take the continuous time signal, convert them to discrete. Once it is discrete, then after what you do, you pass it through a low pass filter. You pass it through a low pass filter where your actual shape is in the triangle, and you get your original thing back. That's the idea. Now see here, by choosing my sampling frequency less than 2W, what is happening? Do I still have my triangle shape intact here? No, the triangle shape is gone, right? So my sampling frequency is now limited by certain factor. Less amount of sampling frequency always means less amount of memory. But then the problem is, see here, author has clearly mentioned some 3 sampling frequency. So this is the case where it took the sampling frequency as thrice the maximum signal frequency. Then the second figure where it took the sampling frequency as twice the signal frequency. This is also fine. This was also fine. In the third case, he took sampling frequency less than 2 omega, less than 2 omega, 1.5 omega. So what happened? The triangle shape in the baseband from 0 to W is now destroyed. Okay, so if at all you want to convert a signal from analog to digital, process in the digital domain, and you want to convert it back to analog, then your sampling frequency shall be at least twice the maximum signal frequency. More sampling frequency is always good, right? The gap is also more, the clarity also more, but then you need more memory. That's fine for us, but less sampling frequency creates this particular problem. Okay, got this particular thing? That is the meaning of the okay. So what happened? If at all you choose the sampling frequency less than twice the signal frequency, you got this problem called as aliasing. There will be overlapped in the shifted replicas of the original spectrum, which is bad. Okay, which is bad. It's called as problem is called as aliasing. The problem is called as aliasing. It should not actually happen. Okay, so the DTFT of the entire thing has been shown here. Okay, now you can see DTF. Now we understand, right? A DTF of a signal usually contains values from periodic, right? So if at all I take a continuous time signal, convert it to discrete, then its DTFT is always P in nature. Okay, it will always periodic in nature. So A here, this is the diagram. You can see in DTFT everything 2 pi actually represents your sampling frequency, right? Everything will be normalized with respect to 2 pi. So for omega equal to twice the signal frequency, spectrum just touch each other. The moment we take sampling frequency less than 2W, the samples, the triangles, they overlap. The triangles overlap and your data cannot be recovered. Okay, so that is the rule for your sampling. Okay, that decides the rule for your sampling. Okay. So that's where my sampling theorem. Okay, so what is the sampling theorem? See here, this is the sampling theorem. Okay, for us to be able to reconstruct a continuous time signal from its samples. Okay, so here is my sampling theorem. What does it say? A band limited signal which has no frequency. Wait a second. Okay, a band limited signal which has no frequency components higher than FM, just the maximum signal frequency, can be recovered completely from set of samples taken at a rate higher than 2W, right? Your sampling rate should be greater than twice the maximum signal frequency. Okay, so this is called as uniform sampling theorem. Okay, this is called as uniform sampling theorem. Okay, if at all I convert the data from continuous to discrete, then the sampling frequency should be such that the rate should be greater than twice the maximum signal frequency. Otherwise, there will be aliasing. Okay, otherwise there will be aliasing. Okay. So here is an example that they have shown. Okay, here is an example that they have shown. This one here, what is the signal? Okay, okay, so x of t equal to cos pi t is a signal. Yeah, author wants us to determine the Fourier transform of the sample signal for these particular sampling intervals, t equal to 1 by 4, 1 and 3 by 2. Okay. So what we will do? Yeah, this got a lot boring, right? We will continue tomorrow. Tomorrow will be my concluding class. Okay, then afterwards I will conduct tests once in 2 days. Tell your friends also right from the first unit. So only tests are the way for you to learn things. Okay. So let me continue tomorrow. It's getting much boring.